Victoria Cam, and I will be discussing quantum weirdness. So this is Schrödinger's equation. Most of us attribute him to the famous thought experiment Schrödinger's cat. So what does a cat have to do with this equation? With quantum physics, with quantum weirdness? What is quantum weirdness? Simply put, it is a world where normal rules and laws fail to explain events. In other words, things get a little bit whack. So at atomic and subatomic levels, traditional laws of physics seem to no longer apply. And as a result, this is the quantum realm, and with it comes quantum weirdness. So this equation models matter as a wave rather than a particle, which is already kind of strange. It ultimately led to a drastic revision of the understanding and representation of the microworld, where everything has a wave function, and that describes a probability cloud of all the possible states. So out of all of this mess, why and how did a cat lead to such radical changes? So we backtrack to 1900, where physicist Lord Kelvin challenged the current theory of heat and light, asking how the Earth can move through an elastic solid and challenging the Maxwell-Boltzmann theory regarding the partition of energy. So this will ultimately lead to the present-day quantum theory. It all began when Max Planck was asked to design the most efficient light bulb possible. Now this inevitably gave way to a fundamental flaw in physics regarding black bodies. So Gustav Kirchhoff asked two main questions. One, how does such a body emit radiation, because it cannot store it all, so obviously some of them has to be emitted. And two, how does the intensity of the emitted radiation depend on its frequency and the body's temperature? Now, thermodynamics actually already gave the answer, but it also implied that the power radiated from over all frequencies must be infinite, and no such body exists. So this actually did not bother him at all, because he didn't believe in the equipartition theorem anyways. So basically he proceeded to fit a mathematical formula to his observations of how energy dependent on frequency, which according to Einstein actually resolved the discrepancy in that energy of the electron should depend on the intensity of light and not its frequency. His assumption assumes light to be a particle, but however, there was, as you already know, compelling evidence that light was a wave. So the big question was, is light a wave or a particle? Well, it has characteristics of both, and guess what? It isn't the only thing to have dual property. So as a matter of fact, all matter does. So matter is, so to speak, a wavicle, and attention quickly shifted from trying to represent a wavicle to finding out how it actually behaved. So Schrödinger quickly found an equation that applies to waves defined over complex numbers, and this states that the quantum wave or quantum waves are linked to pairs of real waves, the complex ocean wave actually has two waves in which they have two different directions of height. So of course it is not as simple, because these waves don't have a fixed shape, and therefore if you can't observe the actual entire wave function, does it even exist? And this basically is where his, so to speak, infamous cat comes in. Imagine a quantum system in a superposed state, such as an electron whose state is either spin up or spin down. When you observe the state, however, you can't really observe the superposition of the electron. You either get spin up or spin down. In addition, once you've observed the state of the electron, then it becomes the actual state of the electron. So this observation forced the superposition to change into a specific component eigenfunction. So the Copenhagen understanding understands it quite literally. The measurement collapsed the original wave function into a single pure eigenfunction. When observing a bunch of electrons, you will observe the states of both states sometimes, and as a result, the wave function can be interpreted as a probability cloud, showing that when you measure it, the probability that you would observe a certain state or a certain result. Of course, this makes it a statistical pattern, not the real thing. Not letting this slide, Schrödinger did contemplate about this interpretation. He acknowledged that it worked on a pragmatic level, but the world around him seemed different. As a result, he invented a thought experiment, the famous Schrödinger's cat. So in quantum mechanics, we have to understand that the decay of a radioactive atom is a random event. However, from the outside, the observer cannot tell if the atom has decayed or not. According to the Copenhagen interpretation, until someone actually observes the atom, it is in a superposition of two quantum states, decayed and not decayed. Similarly, this applies to Schrödinger's cat, the detector, the flask, and the cat all in the box. So until somebody actually opens the box and sees that the atom has decayed, thus killing the cat is in a superposition of two states, being dead and alive. So of course the box is impervious to all quantum interactions, so the only way to find out is actually to open the box. According to the Copenhagen interpretation, once the box is open, the wave function collapses and the cat switches into a pure state, either dead or alive. Okay, so let's add a camera into the box and film the entire thing. That solves the problem, right? Well, not really, because the camera is also in the box and it would require us to actually open the box to see the final fate of the feline. So as a result, generations of physicists were taught that Schrödinger created this thought experiment to show that quantum superposition extended into the macroscopic world, which is the complete opposite of what he meant. He introduced the cat because it put what he considered to be the main issue of sharp relief, for the cat belongs to a macroscopic world, a world in which matter does not behave the way quantum mechanics wants it to. So he was asking why the classical world, the world that we live in, fails to resemble the quantum reality. So why do we not see superposition, and why does the universe look classical? So fortunately, there is some sort of understanding of this phenomenon. The traditional answer is Snell's law, which states that the reflected ray bounces off at the same angle at which it hit. So physicist Richard Feynman states that this is not what occurs in the quantum world. The ray is a stream of photons, and each photon could literally bounce all over the place. If you superpose all the possible things the photon can do, then you get Snell's law. Thus, if you superpose all quantum states for an optical system, then you get the classical outcome in which the light rays follow the shortest path measured by time taken. So the other answer is decoherence. For instance, if you take two superposed states, change the phase of one, and then put them back together, what you get is something totally different. So if you do the same for a lot of these components, the resembled wave can be, quite honestly, anything. Hence, you don't just lose track of whether the cat is dead or alive. You actually can't even tell that it was a cat. So this pretty much solved the fate for the cat. If only the box was totally impervious to all quantum decoherence, can the experiment produce the superposed cat? And no such box actually exists. However, there is this other explanation that goes far beyond the extreme, where one can proceed that the entire universe is a superposition. So according to Hugh Everett Jr., the quantum wave function of the universe is not a pure eigenmode, but a superposition of all possible eigenmodes. So the cat actually does not have to collapse into a single classical observation. It can remain unchanged with no violation at all. So instead, there are two coexisting universes, one in which the cat is alive and one in which the cat is dead. The question is, how do we know that a parallel universe exists? A rather simple explanation is that the formation and evolution of parallel universes involves them splitting off whenever there is a choice of quantum state. So surprisingly, many physicists actually support this many worlds theory. However, the separation occurs at the level of quantum states of constituent particles. So most alternatives actually don't make any sense. A simple alternative to a dead cat is actually not a cat that's alive. Therefore, it is highly unlikely that there exists another parallel universe that makes quote-unquote human sense. As a result, Schnell's law is applicable to any classical world because if it weren't, then the world wouldn't be so-called classical. There is only one classical world from the infinite superpositions at the quantum level, and that is the world in which we reside in. So out of all this, Schrödinger's equation simply defines the evolution of a particle's wave function in time and space. So asserting the wave particles as a probability function, it led to the creation of electron orbits, those that we now see in physics and chemistry textbooks. Furthermore, thanks to his contribution, one could no longer model an atom as simply a nucleus with a few electrons in circular orbits around it, but rather must assume that there is a electron probability cloud that surrounds the atom, hence bringing us to our modern day atomic model. Thank you.